Is it useful? I mean.
Yeah. A lot.
Yeah. Thanks. Okay. So we mentioned that the interpretation of the wave function, standard interpretation, is that the modulus square of the wave function is the probability density for finding the particle at a certain position. So if you have a certain small volume V, okay, and you want to know what is the probability that if you measure the particle, you will actually end up being there, then the integral over this volume of this probability will be just the total probability of finding the particle in the little volume. Okay? Good. Now we would like to understand if this P, in fact, obeys what is called the continuity equation. Now, you are probably used to it from electrodynamics. If you have charges, okay, these charges do not disappear, okay? They move in space. And if you consider the amount of charge in a little volume, you know that the change in the charge is related to the current entering and leaving the little volume, okay? And in fact, there is a well-known equation that is called the continuity equation, which is related to the conservation of charge. Now, we'll try to see what happens to the derivative with respect to time. Notice this is a partial derivative of this P of x and t. How does it change at the given point x, the probability of finding the particle in x, okay? And I want to show to you that you can define, in fact, a new object, okay, which is the current j at x and t, such that the derivative of the probability is equal to the divergence of the current, okay? Is this symbol clear to all of you? Okay? This is a current, so it's a vector. 3 component, and the divergence is simply the derivative with respect to x of j x plus the derivative with respect to y of jy plus the derivative with respect to z of jz. Okay? So this is the meaning of this symbol. Okay. Let's see how we find this thing. First of all, the first step is to notice the first thing is to notice that this is the derivative of P, which is psi star, okay, of x and t, psi of x and t. From now on, I will omit the variables to spare some chalk. And so I would write here the derivative with respect to t of psi star times psi plus psi star, the derivative of psi, right? Rule for the product. Now you remember that psi obeys the Schrödinger equation, okay? So I know that I, h bar, the derivative with respect to t of psi of x and t is equal to h, the Hamiltonian, applied to psi of x and t, right? And this is a Laplacian plus the potential. Is it clear to everybody? Okay. This immediately tells me that if I divide by I h bar, the derivative of the psi is equal to this object, okay? And if I want the derivative of psi star, I have simply to take the complex conjugate of this, okay? So let's write it like this, okay? H psi star, okay? Great. So let's write it. So this is equal to 1 over I h bar. I write it and then you tell me if you understand. So this first term is psi star h applied to psi, okay? From this object, and the 1 over I h bar is in front, and the second one is in fact this with a minus, right? Okay, because the I here, when you take it out of the star, is a minus. Okay, so minus h applied to psi star times psi. Okay, so this is this first term, and this is the second term. Is it clear? Okay. Now, last time, if you remember, we used almost the same steps, but at that time the goal was to understand the total integral in the x of p of x and t, okay? And we wanted to prove that the total integral is independent of time. So the derivative with respect to time was 0. And to understand it, we used almost the same step, except that here there was an integral. Remember? And here there is an integral over x. And if there is an integral, you immediately understand that this is somehow psi, h psi minus h psi psi, so something like this, okay? And since h is Hermitian, this was 0, okay? So this is just to connect to what we did last time. But now there is no integral. So you cannot say here there is an x and a t. You cannot say that this quantity is 0. It is not 0, in fact, okay? In general. Sorry, I'm messing it up, just to show that here there is no integral, there is a point in space and time. Okay, so I want to show to you, well, first of all, let's consider that h is equal to, say, p squared over 2m, so the Laplacian, you remember, plus v of x, okay? Let's consider this term, v of x. How does it appear there? Well, psi star v psi minus v psi star psi. Comments? V is a real potential, remember? Okay, so v is equal to v star. So this is 0. Okay, so the potential does not appear at all. Okay? All you need is the kinetic part of the Hamiltonian. That is the only contribution to this thing. You start understanding, right? The way the probability changes in a given point depends on particles flowing out, which is kinetic energy, okay? That must be. So it's whatever potential, the potential will not appear on the right-hand side. The potential will not appear in the current, okay? It's all kinetic that appears in the current, okay? So, recalling that p squared over 2m is equal to minus h bar squared, the Laplacian, over 2m, okay? Then you can substitute here p squared over 2m, here and here, just do one little element of algebra, and you rewrite the expression there as I h bar divided by 2m psi star, the Laplacian of psi, minus the Laplacian of psi star times psi. Let's see the origin of the terms, okay? Let's make the algebra reasonable. Well, the 2m comes from this 2m, okay? Here I have minus h bar square on top of that. The h bar square cancels this h bar and becomes there. There is minus 1 over I. minus 1 over I is I. Okay? The rest is just the Laplacian applied to psi minus the Laplacian applied to psi star. Okay? Is it clear? Good. Okay. So only Laplacians appear. Now, little piece of algebra. If I have the divergence, okay, remember the symbol, gradient dot, of the following object, psi star grad psi, this is a vector, right? By component, and you can take a divergence of it. Now, it takes very little algebra of vector calculus, really very simple. The derivative x, the x component, you do all your algebra, you understand that this is the gradient of psi star dotted into the gradient of psi, okay, plus psi star the Laplacian of psi. Okay? It must be a scalar quantity. You can make a scalar quantity either by taking the gradient dot scalar product with the gradient of the two terms, or by taking psi star Laplacian psi, which is already a scalar. Notice, this is a bit like if you take the derivative here, you get this. If you take the derivative there, you get this. Okay? So when you have a derivative of a product, remember you have the two terms. So if you do a little bit of algebra, really very simple, but try to do it, okay, you get this. Okay? Now, why do I want to use it? I want to use it because I notice that here I have the Laplacian, which is what I have there. Okay? Now, you can undo this expression somehow in terms of this. So it's almost the divergence of something, except for a term, right? I want to express, the goal is to express it as a divergence of something. It's almost there, except for this term. Now, if you do the algebra, you will realize the term there cancels between the two things, okay? Because it's the grad, it's a symmetric thing, grad psi star, grad psi, and it appears in both terms, okay? So the end result is that this is really equal to minus the divergence, okay, of, let me write it and then we make sense of it. It's minus I h bar over 2m psi star, the grad of psi, okay, minus grad psi star psi. Okay? Let's see why this is so. Okay? Now, when I take the divergence of this first term, you see, this applied to this, I apply the formula and I get grad, and then I get this first term. You see? The first term is this. The coefficient is minus and minus is a plus. Okay? Good. If I take the divergence of the second term, I should do something like divergence of the grad of psi star psi. This is equal, I apply a similar formula to the grad of psi star dotted into grad of psi plus the Laplacian of psi star times psi. Okay? So again, I take now the divergence of this, it has a minus sign, so you see that these two terms in fact cancel, and the minus sign here gives you exactly the second term. Okay? So please redo the algebra yourself, because there is no substitute for actually doing it and understanding that the piece go nicely. Okay? So The potential cancels, you're left with the Laplacian. The resulting expression due to a vector calculus identity is in fact the divergence of an object which involves the gradient. Okay? So somehow I wrote it with this minus sign because I want it to be this, the current density associated to the wave function. Okay? We already commented that P, the probability, is not the full information. Psi is important. And in fact, you realize that if I want to know how P changes, I cannot write an equation which involves P only. It involves a new quantity, which is the current. Okay, the current density is indeed constructed again from psi, but involves derivatives. So not psi star psi, like P. So you see that P is not enough. Psi is the real important quantity, and with psi you construct both P and the current density, which governs the continuity equation for P. Okay? Now, let us finish re-expressing this in a way that is somehow suggestive. Okay? So I write it as, remember that the momentum operator is minus I h bar the gradient. Okay? So you immediately see it that this object here is the momentum operator, in fact. Okay? So I will write this as, so this current here, as I write J as 1 over 2m, okay, psi star, the momentum operator applied to psi. This is the first term. Okay? This term. What about the second term? The second term is equal to the momentum operator applied to psi, and then all star times psi. Notice, I put a plus here, because if I apply here minus I h bar the gradient of psi, and then I take the star, when I take out the I from the star, I get precisely the correct sign, which here is plus, by the way, because there is a minus and a minus. Okay? So it's a plus. So you see, you have to rewrite it in this way, with a plus in between, if you use the momentum. Is it clear? I mean, these are simple things. The only thing that I want to comment is that, you see, momentum divided by mass is somehow the velocity, right? So this object is essentially something which senses the velocity, okay, the density of velocity for the particle. The only interesting fact is that somehow, since applying a gradient to the wave function is somehow something that you can decide to do on the right or on the left, you have to do it symmetrically and take a factor 1/2. Okay? So this is somehow the velocity symmetrized. So you take the gradient to the right and to the left, and you take just half of it. So this is one way of remembering also the expression for the current. Somehow it's P 1/2, P acting to the right, P over M acting to the right, plus P acting to the left. Okay? You have to remember that you have to sandwich P in between psi, but it has to act both on the right part and on the left. Okay, good. Now, you immediately see, by the way, that if I have a function, if I have a function that is real, suppose that psi is a real function, then what you would conclude about the current? it is 0 for a very simple reason, right? Psi star, the grad of psi, if minus essentially its complex conjugate. This is the complex conjugate of this, okay? Would be just 0 if psi is real. Now, luckily enough, if a wave function is obeys the Schrödinger equation, generally it is complex, okay? But we will see very soon that there are special cases, okay, which are called the stationary states, where the wave function is complex but only up to a phase. So we'll discuss this in a second. We'll see a case where somehow the current is indeed a zero divergence for a simple reason. Okay? Let's see, in fact, this example. Okay? So what I do now is the time independent. So I erase some of this. I will now consider I leave some of the derivation for a while. So the time independent Schrödinger equation. Okay? So far I have I, h bar, the derivative of psi of x and t equal to h applied to psi of x and t. And by the way, so far, indeed, h might depend on time. A case where h depends on time, for instance, is, okay, p squared over 2n, so the Laplacian, plus a potential which is a function of space and time. For instance, you put some electric fields and they change. You could consider this. Okay? So the system is not isolated. There are external fields that act on the particle, and this makes the Hamiltonian time dependent. Okay? It's a perfectly reasonable thing. You write still the same Schrödinger equation. No problem. However, there is a special case which somehow needs some consideration, which is when the Hamiltonian is time independent. Okay? So this is a special case. If it is time independent, okay, I would like to search for solutions, okay, which are factorized. So I would like to see if there are solutions that can be written in the form of factorized functions. A function of space times a function of time. Can I find them? This is the question. Okay? This is a general complex function of space and time, and my question is if I can find a solution which is of that form. Okay? And the answer is yes. Okay. I'll give you a solution first, and then we try to reverse engineer or understand why this is so. Okay? The solution is the following. Take functions of this type. Fn of t times phi n of x, where the phi n are eigenfunctions of the Hamiltonian. Okay? As you remember, the eigenvalue analysis that you learned for matrices applies to operators as well. Okay? So you can define an eigenvector of the Hamiltonian, which is an Hermitian operator, to be the object such that if you apply the Hamiltonian, you get back the same functions up to an eigenvalue En. Okay? So this is called the eigenvalue problem for the Hamiltonian. Okay? One can show that this problem not only has a solution, but indeed the solutions that you get for this problem are in general an infinite number, and they form a basis for the Hilbert space. In fact, an orthonormal basis. Basis for the Hilbert space. Okay? So not only the eigenvalues and eigenvectors exist, but they give you a convenient set of functions, okay, in terms of which you can expand any function you want. Is it clear? This is the meaning of a basis. Okay, good. Let us see what happens if I use this ansatz, this guess for the psi. Okay? So, does it satisfy this equation? Let's see. H bar, I should calculate the derivative with respect to time of some Fn of t times phi n of x. Okay? Well, this Fn of t is some so far unknown function of time, which I would like to find. But this should be equal to the Hamiltonian applied to Fn of t times phi n of x. Okay? Now, the Hamiltonian is a linear operator. Okay? So, when you apply it to a function, okay, and you multiply this function by a number, this is a general complex number for fixed t, obviously, you can take this out, right? So this is the same thing as Fn of t times h applied to the function. Okay? Is it clear? Good. But I have chosen deliberately the phi n to be eigenfunctions of the Hamiltonian. Eigenfunctions. Okay? So this object here is very simple. It's equal to a number, which is the eigenvalue associated to phi n, times the function itself. Okay? Good. So I end up having this equation written in the following form. En Fn of t phi n of x. Clear? Good. What about the left-hand side? The left-hand side is equal to I, h bar. The derivative with respect to time now is applied only to the unknown function times phi n of x. Okay? So you see that phi n of x now appears in both sides. Okay? So this equality is satisfied only if the function phi n satisfies, let's see, which equation? I, h bar, the derivative of Fn of t should be equal to En Fn of t. Is this clear to everybody? Okay? So not all Fn of t can be chosen there. They must have a precise form. And the precise form is given by the solution of this equation. Now, this is a very simple differential equation. Linear, and the solution is e to the minus I over h bar En times t. Okay, you can verify this is the solution which at time 0 is equal to 1, obviously. Okay? Now, you can verify if you take the derivative, you bring down minus I over h bar En, and if you multiply by I h bar, you get exactly this. Clear? Okay, so this is the solution. In fact, I can now substitute in here, okay, and I have just shown to you that functions of this type, okay, where, sorry, the chalk is terrible. Functions of this type where phi n are eigenfunctions of the Hamiltonian and the value En there is the corresponding eigenvalue, are indeed solutions of the time-dependent Schrödinger equation. Okay? This solves this. The time-dependent Schrödinger equation. Okay? So by solving the so-called time-independent Schrödinger equation, which is essentially an eigenvalue problem, automatically I have constructed solutions of the time-dependent Schrödinger equation. Okay? Obviously, because H is time-independent, otherwise, or I've said you should throw it away. Okay? Good. Now, you might ask, but who guarantees that these are the only solutions? Well, it's not difficult to actually realize that this must be the only case. Okay? It is basically based on the following argument. Okay? Similar to what I have done. If I have, suppose that I don't know this, I have that I, h bar, the derivative with respect to time of phi n of t times phi n of x, okay, is equal to fn of t h applied to phi n of x. Okay? This is essentially what's written here. I'm not now using my guess that my assumption that phi n is an eigenfunction, but this is still true. Now you realize essentially the following thing. Suppose that this function is different from 0. Okay? Then you can divide everything by phi n, and if this is different from 0, you can divide everything by fn. So you can write something like this: IH bar 1 over fn of t, the derivative with respect to time of fn of t, is equal to 1 over phi n of x, okay, times the application of h to phi n of x. Okay? Assuming that these are different from 0. Well, this equation is highly suggestive. It tells you that here I have a function of time, and here is I have a function of space. How is it possible to reconcile the two things? Only if they are both equal to a constant. Okay? So the question is that there must exist a constant which depends on n, let me call it En, such that h applied to phi n divided by phi n is a constant. And the left-hand side is nothing but the equation I have seen there. Okay? So in some sense, although this seems like something that I invented, after a little thinking, it is almost the only thing you can invent. Okay? Is it clear? Good. Now, recall now that for these solutions, okay, I have that the associated Pn of x and t, okay, which is the modulus square of e to the minus I En t over h bar times phi n of x. How much it is? This is the phase. Okay? So I can get rid of it. This is equal to phi n of x modulus square. Okay? So these solutions in fact have a probability that is independent of t. Hence, they are called stationary state. Stationary because somehow if you look at the probability, it doesn't change. It stays there. Okay? Is it clear? Obviously, since you know that in general the derivative with respect to time of p of x and t is equal to minus the divergence of j, if I ask you what is the divergence of the current associated to these eigenfunctions, it must be 0 because this doesn't depend on time. Okay, so the divergence of the current constructed from this phi n should be 0. Okay? Yeah? They carry no current. And the probability correspondingly doesn't matter. Questions? Okay, good. One last thing. These are spatial solutions, okay? I just constructed solutions that are product of a function of time times a function of space that is an eigenfunction of the Hamiltonian operator. But the general solution is obviously not a factorized solution. So I ask, can I tell you something about the general solution of the Schrödinger equation in this case? And the answer is yes, by using this fundamental fact that this is a basis for the Hilbert space. We'll see examples later on. I don't want to prove the theorem, okay, that if I have an Hermitian operator, I can find eigenfunctions, and these are a basis of the Hilbert space. This is a theorem of mathematics. We don't kind of care, but we will see repeated examples where this holds true, okay? So, in some sense, we accept it. Now, let's see. So, suppose that I give you the following problem. I tell you, find please a solution of this equation which at time t equals 0 is equal to some prescribed function psi 0 of x. Do not confuse the psi 0 with the phi n, okay? This is just a label to tell me that this is a function which gives me the initial time wave function, okay? Whatever it is. The phi n are the eigenfunctions of the Hamiltonian, okay? So I want to solve this problem. A typical initial value problem. I have a differential equation. At time t equals 0, I have some function, and I want to know how it evolves, okay? Okay. Now, how do I solve it by using the ingredients that I have on the blackboard? Step number 1. I express psi 0, okay, in terms of the phi n, okay? How do I do it? I do it by writing it as a sum over n, where n is the label that distinguishes the different eigenfunctions. I write it in this discrete form, although sometimes I have a continuum, okay? So we will see examples of both discrete, continuous spectra, and a mix of both. But let me write it in a simpler discrete form. Some coefficient Cn times the function phi n of x, okay? Who justifies this way of writing? The fact that phi n is a basis, okay? So any function in the Hilbert space can be written as, in general, an infinite linear combination of the function phi n, okay? How do I calculate the coefficients? Okay? You probably know in linear algebra, okay? If I have a vector, okay? Okay, and I have some basis functions, okay? Some basis vector. How do I calculate the components of this vector? I take a scalar product with the vectors of the basis, okay? And I do exactly the same thing here. So, what I do is I take, let's consider the scalar product of phi n with psi 0. I will use now the fact that this is an orthonormal basis. So, if I have phi n prime, this is equal to the delta of n prime. Okay? So it is equal to 1, they are normalized, but if they are different, they are 0, orthogonal. Okay? So let's use this. And in fact, let me transform this. This is a dummy index. So let's write it as sum over n prime. Then I have sum over n prime. The scalar product is linear on the right, so I can actually write this as sum of Cn prime times phi n prime. Okay? But this is a delta, so it's delta of n prime. And when I do the sum over n prime with this delta, this becomes equal to Cn. Okay? So the coefficient Cn or Cn prime that appears there is nothing but the scalar product of the vector that I want to represent with the basis function of n. Okay? Like in linear algebra of vectors in three dimensions. Same thing. And this is what? Well, it's an integral. So in principle, I have to calculate the integral over all space, okay, of phi n star x psi 0 of x. Okay? But is it this simple, difficult? Depends. Okay? It might be complicated to calculate all those functions, but all those integrals, but in principle, it's something that it's not logically complicated. Okay? So the coefficients somehow that appears there are calculable by integrals. Good. Now, let us revert now to the sum over n. Here. Okay? And I recall you that Cn is equal to phi n psi c. So the initial function, I know how to write it in terms of the basis. Fantastic. Now, what I ask you to accept, because we'll prove it in a second, that the function at time t will be sum over n, the same Cn you calculated, e to the minus en t over h bar times phi n of x. Okay? So this is my the thing that I want to prove. First of all, obviously at t equals 0, all these objects are 1, so at t equals 0 this is verified, right? Is it clear? Good. Next, let's verify that this solves this. So we put it here and there. Okay? Left hand side. These are always very, very simple manipulations, okay? Don't expect simple things. But I do it because, well, just to quickly, okay? So I have I, h bar, then I have the sum over n, I have the Cn, I have the derivative with respect to t of e to the minus I en t over h bar, and then this thing is unaffected by the derivative. Okay? This is the left hand side. The right hand side is sum over n. Again, I can, by linearity, oops, I'm sorry. Sorry, there is a call from this side. Pronto?
If we use this to the exercise of the square like a, so if the exercise where you just have a for some, like the sign of x is equal to a for negative x to x. The thing here is that you can choose any basis function. You know, because it satisfies that at sin x of t equals 0 is just a.
Yes, you can choose any basis, but like for example, in that problem, you cannot use the basis of functions which are derived from the integral function.
Yeah, but you can choose. And the thing here is if you integrate it at the outside.
Okay, sorry. So the right hand side, this is a linear operator acting on the sum over n of some constant times this function. So it's sum over n, the constant you put it out, e to the minus I e n, t over h bar, times the operator acting on phi n of x. Is it clear? Okay? Please, I mean, if this is too fast, tell me. Now, this object, being an eigenfunction, is just En times phi n of x. Okay? And on the left-hand side, when I take a derivative, when I multiply by IH bar, from this object here, what you get En times e to the minus I En t over h bar. Okay? So you see that you have exactly the same ingredients. The Cn, the En, okay, the factor here, and the function phi n. Okay? So indeed, once I have solved the time-independent Schrödinger problem and found the eigenfunctions, I express the initial function, whatever it is, in terms of them, by some constants which require integrals, and then it's almost done. I have essentially to glue to the coefficients a phase factor e to the minus En. Now, all this seems a trivial thing, right? However, I mean, first of all, it's considerable work in general, which is not necessarily simple and analytical. Second, you might think that, well, the function changes very little because you simply add, well, not so, okay? Adding to a linear combination of functions phase factors which change in time makes the combination dramatically time dependent, okay? We will see examples of this, and because this is something deceptive. It might seem that, well, it's something that essentially doesn't really influence. No, the function changes in time in a dramatic way precisely due to this simple-looking phase factors. Okay? Good. Questions on this part? Okay. Now, I want to spend 10 minutes on, before we adventure in essentially doing this problem for a class of simple problems. So I will try to find explicitly the eigenfunctions of simple Hamiltonians and the associated eigenvalues, which is called the spectrum of the Hamiltonian. Okay, so the set of all the eigenvalues of the Hamiltonian is called the spectrum. Let's start familiarizing with these names. Okay? Before we adventure in that, let me do a simple exercise. Suppose that I have a free particle. In fact, a free particle in one dimension, so simplified, although you can easily extend all I say in the notes is done for a general three-dimensional problem. But let's do it in 1D, because it's enough to understand the essence of the story. Erase. Well, maybe this part was useful. Okay, so I leave it there for a while. H E n equal to E n phi n. Okay? Let me consider x extra simple case where h is equal to p squared over 2m. Free particle, okay? In 1D, in one dimension. So this is nothing but minus h bar. The Laplacian in one dimension is simply the second derivative with respect to x. Okay? Clear? Okay, good. What are the eigenfunctions of this object? Plane waves. Okay? They're very, I mean, you know that plane waves are eigenfunctions of p. So they are eigenfunctions of p squared. In fact, let's recall. P applied to, say, e to the I kx, let's write it in 1D, is equal to h bar k times the same function. Is it clear? Remember, p is minus I h bar, the derivative, okay? And therefore, you bring down h bar k. So this is the eigenvalue of the momentum operator, and this is the eigenvector. Obviously, automatically, if you want p squared, h applied to the same eigenfunctions, okay, gives me the square of the eigenvalue, so h bar k squared divided by 2m times e to the I kx. Okay? And this is the well-known h bar square k square over 2m. Remember that in the first lecture about the wave packet, we kind of guessed that this should be the correct relativistic dispersion. By the way, this was only a hint of the theory. It was not meant to be a derivation in any sense of the Schrödinger equation. Okay? Someone asked what happens if the wave packet is not Gaussian. Is still true that, yes, it is still true because somehow the theory is there, rock solid, and only what I exemplified to you is just a simple Gaussian wave packet calculation to familiarize with the thing. Okay? So the dispersion is correct in the non-relativistic regime, independently of the form of the wave packet being Gaussian or not. Okay, good. But now let's focus again on this thing. Now, you see the ingredients that I have there. First of all, these functions here, okay, have become now e to the I kx, any k, okay? So I should call them, say, phi of k of x. So now you see that the index has become a continuous index. Okay, you choose a k, and here you have a wave function. So not a sum in some sense, I have, but an integral over k that I should do. But there is a problem immediately. Obviously, En becomes this Ek, which is the usual dispersion, parabolic dispersion. Okay, there is a problem, however. These objects do not belong to the Hilbert space. They are not normalizable. Okay? So somehow we are seeing a case which we will repeatedly encounter of a continuous spectrum. You see, any value of energy, okay, from 0 to infinity is actually possible as a value as an eigenvalue of the Hamiltonian. In fact, for every value here, you have two eigenfunctions, one with a positive and one with a negative sign, e to the plus or minus I k x. Okay, this would give me exactly the same eigenvalue, right? So any non-negative real number belongs to the spectrum of the Hamiltonian, but the eigenfunctions are functions that extend over all space. They are not normalizable. Okay? Not normalizable. This is a very, very common thing. Okay? Whenever we will have a continuous spectrum, always think of plane waves extending everywhere. They are not exactly plane waves, but in essence, they are functions that visit the whole space. Okay, how do you make sense of this? Okay, so I want to teach you a little device that people use a lot in condensed matter, which is called the periodic boundary condition trick. You do the following. You take your system and you put, rather than working in infinite space, you work on a finite interval, okay? Let's do it symmetrically, say between minus L over 2 and L over 2, okay? This is my space. It has a certain length, L, and not infinite. And I pretend that the functions I look for are functions which are periodic with period L. So the functions I look have to respect this. Okay? Is it clear? So whatever I have here will be repeated here. Okay? Because the function of x plus L and x are the same. Clear? Now, suppose that I tell you, solve the free particle with this so-called periodic boundary condition. They are often abbreviated in this way. Periodic boundary condition. Because, I mean, you assume that the function is periodic with a given period L, which I decide, okay? It's a free particle, there is no. But I put it in a box with periodic boundary condition. How do I solve the problem? Well, you know that the problem is solved by functions, okay, which are plane waves. So the only thing that you have to look for are what are the plane waves that give you a periodic function like this, right? What is k to be periodic? Well, let's see. I want e to the I k x plus L should be equal to e to the I kx. Is it clear what I wrote? I took away a plane wave and I hardly imposed that the periodic boundary condition written here is verified by the plane wave. Okay? And now you realize that this object here cancels, but this is true if and only if e to the I k times L is equal to 1. Is it clear? Okay? So what are the possible values of k? K times L should be equal to 2 pi times an integer. Any integer from minus infinity to plus infinity. Okay? Good. Or k is equal to 2 pi over L times n. Again, n equal to from minus infinity to plus infinity. It is called the z. Okay, the integers with the sign. Okay. Now, you see that the k's are no longer a continuum. The corresponding energies, remember the energies Ek are h bar k squared over 2m. You can substitute, these are h bar squared over 2m, 2 pi over L squared, n squared. They are also discrete. Okay? So for n equals 0, I have 0. Then I have the first object, which is in fact doubly degenerate. There are two eigenfunctions, one with 1 and one with minus 1, which have the same energy, and so on and so forth. Okay? This is 4 times as big, 9 times as big. And the spacing, okay, this spacing here is governed by 1 over L squared. So if you send L to infinity, the spacing becomes infinitesimally small, and all these discrete energy levels become again a continuum. Okay? So this is kind of a trick to say, I want to deal with functions that are somehow well behaved, and I want to somehow normalize things in the right way, but in the limit in which I take my boundary condition box to be infinite, I would recover what I need. Okay? Let's insist a little bit more on this fact. Okay? So, what functions, how would you normalize the function on a box? We would say, okay, the normalization is the following. So rather than writing phi k equal to that, let me write phi. This chalk is terrible. I write phi k tilde of x equal to 1 over square root of L e to the I k x. Notice the factor 1 over square root of L. Okay? Now, what is the use of this 1 over square root of L? If I try to calculate phi k prime with this tilde, notice the symbol here. Is the scalar product calculated only in the space of length L, which I depicted there. So this is what? This is the integral from minus L over 2 to L over 2 in dx of 1 over square root of L from here, 1 over square root of L from here, and then I have e to the minus I k x from here, and e to the plus I k prime x from there. So this integral is equal to 1 over L, integral from minus L over 2 to L over 2 in dx of e to the I k prime minus k times x. Okay? How much is this? Yeah, but can I ask you why?
Because if k equals to k prime, then the integral is 1, and if it doesn't, it's 0.
Yeah. Let's see for a second why it is. Well, if k is equal to this is k prime, this is 1, right? So this is the integral is just 1. Let's try to understand why it is 0 if the two wave vectors are different. This object is, remember k is 2 pi over L times n. So this object is e to the I 2 pi over L n prime minus n times x. Okay? So you see quite clearly that this is essentially cosine of this object plus I, the sine of this object. But you immediately realize that the cosine and the sine are periodic function exactly in the intervals where you are looking at. And therefore the integral vanishes. Okay? The only one that doesn't vanish is when n prime is equal to n, because at that point is 1. All the others are just 0 because you are integrating either a cosine or a sine in a period of the trigonometric function. Okay? Is it clear? Fantastic. So this is the promised Kronecker delta, which we said we would have. In fact, now these are discrete functions, pretty much as I wrote there. Discrete functions which are normalized. Okay? So we like them. Fantastic. Good. Now, I told you that there is a theorem by which you can expand any function into eigenfunctions of any Hamilton operator. Now, here we have free particle. What does it mean, that theorem, in this specific context? It means the following, that I can expand any function in terms of these objects. Well, any periodic function, obviously. Well, this is a Fourier expansion. Sine and cosine, okay, including the constant, in this interval here. Okay. So I have essentially the Fourier series. Okay. So the Fourier series reads as follows. I have a psi of x, which is a periodic function in this region, and I write it as the sum over this k, okay, of the phi tilde k of x times a coefficient. How do I calculate the coefficient? We already did. Remember? The ck would be phi tilde k times psi. Okay? Good. So, what is it? Well, so let's see. This is the sum over k. Here there is a 1 over square root of L e to the I k times x. And here, well, let me add a further 1 over square root of L and then square root of L times phi tilde k psi. You might say, what do you do? You add them. Well, I can always do that. It's useful. Believe me. Follow me for a few minutes and you will see that it is useful to write it in this way. Now, I write here that k is equal to 2 pi L times n. All right. What am I doing here? I'm writing this as 1 over L, because of these two factors, sum over k e to the I kx, okay, times a coefficient, which has included this factor here. This coefficient, I would call it psi of k, okay? After all, I want to express a psi of x, and I invoke a coefficient that is called psi of k, to remind me. So what is psi of k? Let's calculate. Psi of k is equal to square root of L times the scalar product, so the integral from minus L over 2 to L over 2 of 1 over square root of L e to the minus I kx times the function psi of x. Is it clear? Now you see why I included that, because in this way this just cancels, okay? And this is the integral from minus L over 2 to L over 2 of e to the minus I kx psi of x, okay? So for k equals 0, this is just the average of the function. For k different from 0 is the cosine or the sine component of the Fourier series, because after all, this is nothing but a series of sine and cosine of multiples of the fundamental frequency, so to speak. We are not in time here, but this is the fundamental Fourier wave vector in this case. Okay, 2 pi over L. And all others are multiples of this, okay, including the 0, which is the constant part. Is it clear? This is the Fourier series. So the theorem somehow is telling you that if you want to expand any periodic function in a finite interval of length L, you can do it with the Fourier series. All right? Now the question is, what happens to this Fourier series when L goes to infinity? Okay? This is now the next step. I want to now explicitly take the limit L going to infinity. What happens? Well, you perhaps guess. We will go to a Fourier transform. Let's see it in detail. Okay. First of all, I ask you to let me introduce a new object still related to this, which is this, phi k of x equal to 1 over square root of 2 pi e to the I kx. Okay? So it's almost the same as this, but there is no L and there is a square root of 2 pi. Why do I do that? Follow me for a second. Now, look at this. Where do I do it? Here. suppose that I ask you to calculate now phi k prime, again on a finite volume L. You might say, we did already this, okay? This is nothing but L over 2 pi times phi tilde k prime, right? This one. They just differ by factors of square root of 2 pi and square root of L. So if you just follow, just look at it, it's equal to this. And I know what this is. This is the Kronecker delta, right? So this is equal to L over 2 pi times the Kronecker delta of k prime. So what I want to convince you is that when L goes to infinity, this Kronecker delta, which remember is 1 or 0, multiplied by L, which is increasing a lot, becomes the famous Dirac delta. Okay? This is the Dirac delta. So it's something that is 0 or infinity. And it enters into integrals, while the Kronecker delta enters into sums. Okay? So in the limit L to infinity, the Kronecker multiplied by L, a large factor, will become a Dirac, and the sum will become an integral in such a way that this does precisely what the Dirac delta should do. Okay? So let's verify this, and we are done. Almost. So to verify, indeed, that this is what you get when you send L to infinity, let me do the following consideration. First of all, maybe I should just suppose that I have a sum, okay, 2 pi over L, the sum over k, where this k are exactly the objects that I wrote there, of some function of k, and I ask you, what is the destiny of this object in the limit L going to infinity? Okay? What I want to argue is that this is nothing but the integral of the function f of k. Why is that? Well, you remember that if I have an integral to calculate, I can do the integral by discretizing with Riemann sums, okay? And as long as I make the subdivision smaller and smaller, the Riemann sum, say, converge to the integral, okay? So if I want to calculate the integral of this function f of k, all I need to do is to section the space into small intervals of length 2 pi over L, which is the difference between the various k vectors, you see, okay? It's exactly the spacing of the different k. So this is k equals 0, 2 pi over L, 4 pi over L, and so on and so forth. So this is the discretization I wrote there. And rather than calculating the integral, you just approximate it with exactly this expression. The length of the interval, 2 pi over L, times the value of the function at the point. Okay, so I'm approximating the integral with this Riemann sum, the sum of the little rectangles times f. Is it clear? Okay, so in the limit L goes to infinity, this Riemann sum goes to the interval. You accept this, right? Is it clear? Good. If you accept this, let me just do one little thing. Where should I do it? Let's see if I can do it here. Okay, let's consider now, I want to still to prove this, because Dirac is always a slightly uncomfortable thing for many of us. No? So, let's see. f of k, I can certainly write it as 2 pi over L, the sum over k prime of f of k prime times L over 2 pi times the delta of k and k prime. Is this simple to understand? Of course. 2 pi over L and 2 pi over L cancels here. The sum over k prime with the Kronecker delta gives me f of k. Good. Now I ask you the following thing. What happens to this object here when L goes to infinity? And what happens to this object here when L goes to infinity? Somehow they should become something, okay? According to what I told you before, this is 2 pi, the sum of a function, so it should become an integral, right? Of some f of k prime. And this object should become something such that the integral of this function over k prime is just f of k. And this something must be the Dirac delta. You realize? Only with the Dirac delta, when you integrate over all k prime, you get f of k. Okay? So this somehow concludes the argument behind the fact that a Kronecker delta multiplied by a big constant L really approaches the Dirac delta. Is it clear? Okay? So it's a little, it's like a game of factors, okay? But the game works perfectly well. So, in some sense, from L going to infinity, I have objects that become from Kronecker Dirac and from sums integrals, okay? And the only very last thing that I would like to show to you is the following. This, remember, was the psi of x, okay? The Fourier series. What happens to the Fourier series? Where is the coefficient? The coefficient is here. This is the psi of k coefficient. So let's see what happens to the Fourier series. And then we stop. Well, this becomes what? Remember? It becomes the integral over dk divided by 2 pi, because there is no 2 pi here, of e to the I kx times psi of k. So for L going to infinity, your Fourier series becomes an integral, which looks like that. What is psi of k? Well, it's written there. But psi of k for L going to infinity is nothing but the integral from minus infinity to plus infinity of e to the minus I kx, the function psi of x. Okay? What is this couple of equations? Inverse and direct Fourier transform. Slightly unsymmetric, you see? There is a 2 pi in the k and no 2 pi in the x. The mathematicians prefer a symmetric version where you put the square root of 2 pi here and square root of 2 pi here. But this is just a matter of taste. Okay? Is it clear? Okay. So good. So we can make sense of plane waves in a finite volume with periodic boundary condition, as long as when we want to take the limit of an infinite volume, we do appropriate changes. So the sum over k's become integrals, the Kronecker delta multiplied by L becomes Dirac, and the Fourier series or whatever become Fourier transforms. Is it clear? Okay. So one last thing before we go to doing other problems, which we will do tomorrow, is a first glimpse of possible misunderstanding with the interpretation of the wave function. Okay? 5 minutes, just to point out that you should be careful with the interpretation of a wave function. Now, Suppose that I do the following experiment. It's depicted here, okay? I prepare some particles, electrons, whatever, and I send towards an obstacle, and this obstacle is capable of scattering the particle partly around this direction and partly without scattering. So it partly goes forward and partly is scattered orthogonally. Okay? Now you might say, how do I do that? Well, in fact, with photons, this would be extra simple. If I take a photon and I send it into a semi-transparent mirror, then there is a probability that the photon goes through the mirror, and the probability that the photon is just scattered, reflected by the mirror. Okay, so this is something that people in quantum optics do every day. In all the configurations of quantum optics, there are mirrors that do exactly this. Okay, just to make, in fact, the experiment that I'm going to describe was actually done with photons rather than with particles. But the idea is pretty similar. So here I have a detector, D2, and here I have another detector, D1, that destroys particles. Okay? Once the particles get to the detector, they are not there. Could be for electrons, some photographic thing or whatever. Okay? Something that kills the electron and reveals it. Now let me arrange for the fact that these are exactly the same distance, okay? And the scattering and transmission probability are exactly 1/2 and 1/2. Okay, so the particle can, say, split into exactly two equal components, transmitted and scattered. Okay, these are two different and separate regions of space where these two detectors are. Okay, so the question is here. So if this is psi, we'll go some psi1 function, okay, around this detector. And here, psi2 function, right? And obviously, the integral, okay, of these two things, total, would be just 1, okay? So essentially, if I ask you what is the probability, okay, P1, that this is the particle is in the first detector or in the second detector, they are exactly the same, and they are just 1/2, okay? Because the wave function is split in two. So, okay, the question is, how should I think of an experiment where I count the coincidence? Okay, you have a detector. Okay, so a particle comes, goes, okay, reaches in equal time here and here, and you might suspect that the function psi of x is in fact a superposition of this plus that, okay, and that there are events where I see the detector just hitting in both D1 and D2 in coincidence, okay? Is this the correct interpretation? So the question is it true that when the electron goes here and then there is a probability 1/2 of going there and there, actually you find a coincidence tick? So you see, if D1 ticks, D2 ticks as well. Okay? Is this the correct interpretation? The answer is apparently not. Okay? So don't think of this as really the electron splitting in half. Psi of x and t gives you the probability of measuring the electron, but the electron will always be either here or there, never in both places. Okay? So if you ask the delicate question, would the two detectors signal in coincidence the arrival of an electron? The answer is never. Okay? Either here or here, but with exactly equal probability. So you don't know where the electron will end up. Will end up either here or there. Half of the time here, half of the time there. But certainly entirely in one of the two places, not half and half. So you might think of this in a misleading way, like the Schrödinger cat, half dead, half. So the wave function as being a superposition. In some sense, if you visualize these functions as a complex field moving in space, you might think, oh, part is here, so maybe the two detectors will actually click. The answer is no. Okay, so the interpretation of the wave function is slightly subtle. Okay, it is in this context a statistical interpretation. So psi describe for me what happens to an ensemble of precisely and identically prepared systems which are scattered by my apparatus, and it gives me the probability of measuring events in this ensemble. Okay, so it should not be intended as a real wave that it spreads in two, and so you have a certain there are electrons that are half here and half there. Okay, the electron is not happy to be halved in two. So when you find it, it's either there and there. It's the same with photons. Okay, the photon can just be transmitted by the semi-transparent mirror or reflected, but not half photon and half photon. Okay, always the entire of it. Okay, so this is just to avoid possible misunderstanding with the interpretation. Obviously, the theory of measurement is a very, very delicate thing. These are distractive measurements. They are now much more sophisticated. When I say now, I mean since the 70s. It's an incredible thing how the technology with which you can control individual quantum systems, okay? For instance, photons in a cavity resonator, like Haroche has done in Paris, and he won the Nobel Prize for that. So you are now able to actually measure things without destroying them, and you can address the destiny of individual quantum states. Okay, so the whole field of measurement in quantum mechanics is really very, very active in some sense, beyond somehow the philosophical implication. There are actually practical ways of how to detect very, very weak effects on a quantum state, to do measurements, sensing, and all these very nice things. So this is just a brutal first application where you destroy things. You should not misunderstand the meaning of the state, okay, as being half an electron somewhere and half an electron in another place in this kind of experiment. Okay, so we'll revert to some of the aspect of measurement later on, but I wanted to somehow make sure that the starting point is not misunderstood, at least. Okay.